Hello, and welcome to the third lecture video for lecture 24. In this lecture video, we're going to talk about Compton scattering, but first I want to explain a few other formulas that help set the stage. So let's take a look at the formulas that are directly below the two that we just discussed for the photoelectric effect. The three formulas that we're going to look at in this video are the ones here, with the primary focus being on the Compton scattering formula at the bottom. Okay, so what's the formula at the top? Well, this is the momentum of a photon. So P, the letter we always use for momentum, is, in this case, referring to the momentum of a photon. Again, this is a topic we've seen before, such as when we discussed solar sails. Okay, so momentum of photon. Okay, that is going to be equal to the energy of the photon divided by the speed of light. The idea of a momentum of a photon was also shown through special relativity at the very end of that chapter. So in a sense, it's the third time we discussed the momentum of a photon. And if the momentum is the total energy of the photon divided by the speed of light, we know that the total energy is Planck's constant times the frequency. So then momentum must be Planck's constant times frequency divided by the speed of light, which comes out to just be Planck's constant over lambda. Okay? So if you know the wavelength of a particular photon, in other words, its color, then you can discuss its momentum. Because although light does not have mass, it does have momentum, as special relativity proves. Okay? Now this next formula refers to the frequency of light that's emitted when an electron is accelerated. Okay? So here we have a charge of an electron. Right, so charge of an electron. Okay, the delta voltage or delta V refers to the change in voltage or the acceleration voltage. Acceleration voltage. Okay, so the idea is that this is just how much kinetic energy an electron would have, and then that kinetic energy of the electron can be changed if the electron is turned. Because the idea, based on electromagnetism, so this would be back to Faraday's law and everything we learned in our electromagnetic chapters, if an electron takes a curved path, it is by definition accelerating. If it's accelerating, then we have a changing electric field, which creates a changing magnetic field, so there must be light produced. So anytime an electron takes a curved path, it emits a photon, okay? And the emitted photon, due to the accelerating electron, would have a maximum frequency, given by this, or a minimum wavelength. All right, so let's label both of those. All right, so this is maximum frequency or minimum wavelength of photon released when electron is accelerated. So here we're going to take a more conceptual look at this idea. I don't have any examples that highlight this particular phenomenon. Instead, I bring it up only to serve the purpose of setting the stage for the next formula. Because if an electron can be accelerated and emit a photon, and a photon has momentum, then it can be shown that if a photon crashes into an electron and that photon is deflected, then the electron will be deflected as well. So essentially you can crash an electron and photon into each other in a collision sort of way. Okay, essentially a fully elastic collision. And that brings us to Compton scattering. Okay, so this line here refers to Compton scattering. So this whole formula, let's label it like so. Okay, so this is Compton scattering.
We need to sketch in several rectangles.
Okay.
We can do this
And when we look at Compton scattering, we have a change in
the
wavelength.
area of these individual rectangles.
Lambda minus lambda naught. Okay? And that is the final wavelength minus the initial wavelength. Okay? And this would be the final wavelength of the light minus the initial wavelength of the light. And that is going to be equal to the change in the energy of the electron. Okay? So let's go and label the rest of this. Okay? So this is the, we'll call this the final scattered wavelength of the photon. Final scattered photon wavelength. Okay, this will just, and lambda naught is the incident or initial wavelength. Okay, h is obviously Planck's constant. M is the mass of the electron, because here we're crashing photons into electrons. Right? C is the speed of light. And then phi is the scattering angle of the electron. Okay? It is, let me rephrase that. It is actually the scattering angle of the photon. And here I have it listed as theta, not phi. So let me refer to my angles correctly. All right? So theta is the scattering angle of the photon. So this is sort of a condensed version of an elastic collision. We're not going to be approaching these collisions in the full way that we might in a traditional 2D conservation of momentum collision. And that's simply because some of the other effects are more complicated. So we're only focusing on the scattered photon. All right, so let's take a look at an example.
Then add up those areas.
All right. So the example I want to show you is example 8. I'm going to leave example 9 for practice, so I'm just going to do one example here. All right. So in this one, we have example 8. A photon with wavelength lambda equals 1.111 times 10 to the negative 10 meters scatters from an electron that is initially at rest. Okay? And what must be the angle between the direction of the scattered photon and incident photon if the speed of the electron after the collision is 8.553 times 10 to the 6 meters per second. Okay? So about 8.5 million meters per second. Still not relativistic speeds here, so nothing to worry about there. Okay? This light obviously has a very short wavelength. Conceptually, that's an important part of Compton scattering. Compton scattering, the delta lambda is so small that it wouldn't be measurable for visible light because it would just be a 1/100th of a 1% difference in the color or in the wavelength. But for a very short wavelength light, it is an appreciable difference in the wavelength of light, thus measurable. And so the type of light that we're talking about here are X-rays. So Compton scattering is done with X-rays. So historically speaking, X-rays had to be discovered first before the ability of light to scatter was discovered later. Okay. So first of all, what we want to find here is we want to find out the energy of the electron after the collision. Okay? So we want the energy gained by the electron. Let's change colors. Energy gained by the electron. Okay, so that's going to be E for electron, little e for electron. 1/2 mass of the electron, and then the final velocity of the electron squared. 1/2. 1.11 times 10 to the negative 31 kilograms. That's the mass of the electron. And the velocity that we're given. Okay, and so that's going to give us 3.3 times 10 to the negative 17 joules. I know the need some space here, so I'm going to fit this in one line actually. There we go. There's a zoom that shows everything. Okay. And we know that the energy gained by the electron must be lost by the photon, because there's nowhere else for energy to go here. There's certainly not heat at the scale of individual photons and electrons. The heat is made by photons and electrons. Okay? So, say thus, delta E for the photon is going to equal delta E of the electron. Okay, and here this is, it's a loss of the energy right here. I'm just looking at the magnitude of the energy, but obviously it's losing that much energy. Okay, and so then the photon's losing that much energy. So then we'd have hc over lambda minus hc over lambda prime equals the energy of the electron. Okay, so what I'm saying there is that is the change in the wavelength. Okay, because if the photon is losing energy, the only way it can lose energy is to have its wavelength increased. Again, this is just the energy of an individual photon. It's just h times f. Okay. All right. So I'm just going to solve for lambda prime, the new smaller wavelength of the photon. So then lambda prime will be hc over lambda minus the final energy of the electron. Going with the reciprocal of that, so I'll go ahead and raise it to the -1 power, and then multiply by hc. Okay, I won't plug in the numbers here, they're just in the interest of space, but if we plug in all the values, and again we know what all the values are, we just plug in the wavelength, Planck's constant, speed of light, and the energy that we solved for, the energy of the electron, we end up with a wavelength of 1.132, excuse me, times 10 to the -10 meters. So indeed it's a longer wavelength, because now the photon has become a lower energy photon. It gave up some of its energy. Okay, so now we go on to Compton scattering. Okay, so thus lambda prime minus lambda, Planck's constant, over the speed of light times the mass of the electron, times 1 minus cosine of phi. Well, now we have everything we need in order to solve for phi. So I'll just isolate phi. Obviously, I get cosine inverse. Okay, and I'm skipping the algebra here. Make sure you can do it yourself. Okay, wavelength's constant, and that's the longer wavelength minus the shorter wavelength. All right, and that gives us 82.5 degrees. So it's a huge amount of scattering because the photon lost a significant amount of energy. Okay, obviously it could scatter more. It could scatter up to 180 degrees if it was kicked back. But still, this is a large scattering angle in the scheme of things, almost at a 90-degree turn. All right, but there you go. So we had to find the energies, relate the energy to a change in wavelength, and then finally use the Compton scattering formula to find that new, angle that led to that new wavelength. Okay, all right. So thank you for watching.